Hello, chemistry students. Today we're going to talk about shielding and nuclear charge. Now you're probably like, well, what do those words even mean? Well, right now we are studying the periodic table, and as you know, the periodic table is made up of boxes that have these elements that are listed inside of them. And scientists use the periodic table to predict how elements are going to behave in chemical reactions. How are they going to bond? How are they going to react with water? By understanding the trends or the patterns among the elements on the periodic table, scientists are able to make those predictions. So we call these patterns trends. Now, as you've already learned, we have columns on the periodic table and we have rows on the periodic table. Columns on the periodic table are called families, while rows, which run left to right on the periodic table, are called periods. And families have patterns that are different from periods. Now, we call these patterns trends. Now, if you think about life outside of the chemistry classroom, I'm sure that you can figure out some other things that you've experienced that exhibit trends as well. Like there are trends in the stock market or trends in the housing market. There's trends in climate change. And all of these different trends, all of these different patterns are driven by certain factors. For instance, supply and demand will cause the patterns that are seen in the stock market, the same with the housing market, while carbon emissions are the factor that will drive climate change, among other things. Well, when we talk about trends in the periodic table, the factors that affect these patterns, that drive these trends, are shielding and nuclear charge. Shielding affects the patterns that are found in families. Nuclear charge affects the patterns that are found in periods. So we're going to look at both. So you should pull up this document. This is called Shielding and Nuclear Charge Notes, Remote 2.0. And our first section is Trends in Families are caused by shielding. So number 1 says to study the diagrams that are found on the next page. So let's move down to the next page, page 2. And you'll see that I have some Bohr models of different elements pictured here. And the first element that I have at the top is hydrogen, and that's in period 1. And then it tells you the number of protons, the number of valence electrons, and then we have the Bohr diagram here all the way off to the right. So the elements that we're looking at are hydrogen, lithium, sodium, potassium, rubidium, and cesium. And there's even another element that's found at the very bottom of that column. But if you find these elements on the periodic table, you will see that these elements are all in the same column, which means that they're all in the same family. So for number 1, we should write that the elements are in the same family. And I do not want Times New Roman. All right, there we go. So number 2 says, what do you notice about the Bohr models as the atoms get larger? How is the model for hydrogen different than the model for cesium? So back to my picture, hydrogen is at the very top and cesium is at the very bottom. So we're looking at the Bohr diagrams for each of them. I think that the first thing that should strike you is that the Bohr model for cesium is much larger than the Bohr model for hydrogen. And the reason why is because cesium has 6 energy levels, or 6 rings around the nucleus, while hydrogen only has 1. Now remember that the period number that the element belongs to tells you how many rings or how many energy levels there are around that nucleus. So I didn't even have to count the ones for cesium. I could just look at my chart and say, oh, it's in period 6, so I know that it's got 6 energy levels around that nucleus. And the reason why cesium has so many energy levels around the nucleus is because it has a lot more electrons than hydrogen does, and so it needs places to house those electrons. So cesium is a bigger atom because it's got many more electrons, and it therefore must have many more energy levels. And like, look at the diameter of each energy level as you move outward from that nucleus. The diameter of each subsequent energy level has to be bigger in order to like go all the way around all of the other energy levels. So that is what we are going to write when we go back up to answer question number 2. So question number 2, what we were talking about is that cesium, which I will abbreviate CS, has more electrons and more energy levels. And it's a larger atom. Okay, so questions number 3 and 4 are asking us which element, and again, remember we're talking about hydrogen and cesium, which element has its valence electron closer to the nucleus and which one has its valence electron further from the nucleus? Well, all you have to do is take a look at our drawing here, at our Bohr model. So here's the valence electron for hydrogen, and remember that valence electrons are the electrons that are found in the outermost shell. And then the valence electron for cesium is way out in the 6th energy level. So I think that your answer is clear. Cesium's valence electron is further from the nucleus than hydrogen is. So your answer to number 3 is hydrogen, and your answer to number 4 is cesium. Now, number 5 asks you which electron is most likely to be lost, the one that's furthest away or the one that is closer in. Now, in class, I was talking about one of your classmates had a can of Monster on her desk. And I said, you know, if I was going to run up to her desk and try to grab that Monster, what would she do to prevent me from grabbing that Monster? Well, she would take that can and she would pull it in closer to her body so that she would be less likely to lose it. So think of these valence electrons as a can of Monster, right? The closer the can of Monster is, the closest the valence electron is to the nucleus, the more difficult it is for that electron to be lost or to be taken away by another atom. So the electron that is further away from the nucleus, that is the electron, the valence electron that is here in the outermost shell of cesium, is more likely to be lost because it's further away from the nucleus. Now you're probably wondering, well, why does that matter? Well, remember that nuclei have a positive charge and electrons have a negative charge. And so opposites attract, right? So the nucleus is going to attract all of these electrons. But the nucleus in cesium has all of these energy levels around it, pushing the valence electron further and further away. So that nucleus is not going to be able to control or to have control over that valence electron, not as well as our hydrogen nucleus does. Even though our hydrogen nucleus is small, it has only one proton. It's only got one ring around it. So it's going to be able to attract and hold on to that single valence electron very well. So here are the answers that you should have on page 1 of your handout. All right, now let's take a look at the bottom of page 2. We are talking about shielding. And once again, shielding is going to occur when you add more and more rings, more and more energy levels around the nucleus. And the reason why you're adding more and more energy levels is to accommodate more electrons. The whole reason why you have to add another energy level around a nucleus is because the one below it was full with as many electrons as it can hold, and so you need to add another ring around there in order to accommodate the other electrons. So I know that we're not looking at the top of the drawing, but I think that looking at potassium, rubidium, and cesium will do just nicely. So as we move down a family, what is happening to the amount of shielding? Well, potassium is in period 4, and we have 4 energy levels around the nucleus. Rubidium is in period 5. It has 5 energy levels around the nucleus. And then cesium is in period 6. It has 6 energy levels. So I think that it's very clear that as you move down a family, the number of energy levels goes up, and therefore so does shielding. So shielding is going to increase as you move down a family. Now, number 7 is asking us to circle the appropriate words in order to make the statement true. So as shielding increases, valence electrons are pushed further from or pulled closer to their nucleus. Well, let's examine that. So here in our drawing that we have, our valence electron for potassium is out in energy level number 4, while rubidium's is in energy level 5 and cesium's is in energy level 6. That means that rubidium's valence electron in energy level 6 is further away from the nucleus than rubidium's or potassium's. So as you move down the family, and as shielding becomes greater, you are pushing that valence electron further away from the nucleus. And as we've already established, the further an electron is from the nucleus, the easier it is to lose. So that is your answer to number 7. As you add more and more energy levels around the nucleus, you're pushing valence electrons further away from it, and therefore they are more easily lost. So shielding increases the likelihood that electrons can be lost. Number 8 asks, what happens to the number of protons as you move down a family? Well, if you take a look at your periodic table, you will see that as you move down a family, well, let's go back and look at our chart here. As you move down the family, what's happening to our number of protons? Hydrogen has 1, lithium has 3, sodium has 11, and we keep increasing our atomic number. So as we go down a family, the number of protons goes up. The number of protons increases. So in our next paragraph, it says, the nuclei of atoms are positively charged because nuclei contain positive particles, the protons, and neutral particles, the neutrons. You'd think that larger nuclei, like those at the bottom of families, would hold valence electrons tightly, but they don't. And the reason why is because if you increase the number of protons in an atom, the number of electrons has to be equal to that number. So as protons go up, electrons go up, and so do the number of energy levels that are required to house those electrons. As you increase the number of energy levels, the attraction between the nucleus and the valence electron, because now you've pushed that valence electron so far away, the attraction between the nucleus and its outermost electrons is lowered, is diminished. So the attraction of the nucleus to its valence electrons is blocked by the energy levels. Big nuclei with lots of energy levels around them don't attract electrons very well. The point is, shielding trumps nuclear charge. You can have a very big nucleus, but if you've got a lot of energy levels around the nucleus pushing that valence electron very far away, you're not going to have the attraction there, and those electrons are easily lost. The consequences of this are listed on your page. Therefore, the valence electrons of large atoms are far from the nucleus. The valence electrons of large atoms are easily lost. The valence electrons of small atoms, therefore, are close to the nucleus, and they are difficult to lose. So those are our notes on shielding in families. I'm going to stop this video here, and I will continue with a second video to talk about the factor that affects trends in periods, which is nuclear charge. Thanks for watching.